All right, so we're going to look at our last type of function that we're going to study before we start trig, which will be next academic week, and that's logarithms. So logarithms are connected to exponentials in that they are the inverse. So another example of an inverse that's more familiar, think of squaring and square rooting. Those are inverses of each other. Logarithms and exponentials are also inverses of each other. And whenever you graph two functions that are inverses, they are mirror images of each other. But not mirror images over the x-axis or the y-axis. That's how we think of mirror image, like reflections a lot. They are mirror images over the line y equals x. Okay. And I've got a picture. I'm going to show you an exponential, and then I'll show you a log. There you go. Now, the calculator can't draw logs perfectly. It does have a little bit of trouble, and that's because logs get very steep, right? Towards, in this case, towards the left side. So we know that when a function starts to get steep, the calculator kind of gives up on it. But that's what it should look like. Okay, this line in black is the line with a slope of 1 and a y-intercept of 0. It's y equals x. If you could fold this right on that black line, the graph in blue would land exactly on top of the graph in red. Okay, they are mirror images of each other. What kind of asymptote do the graph in blue have? Yep.
Y equals 0.
Yeah, so specifically it is y equals 0. It had a horizontal asymptote. Well, the graph in red, which is the log, that also has an asymptote. What kind of asymptote does it look like we have in the red graph? We have a vertical asymptote. So basically with logs and exponentials, everything switches place. Whatever was y becomes x, and whatever was x becomes y. It all switches place. So think of exponentials. What's the domain of the graph in blue?
All real numbers.
All real numbers. It goes left and right forever. What's the range of the graph in blue? Yep.
Parentheses 0, comma, infinity.
0 to infinity. Okay, we did that on Monday. Now let's compare that to a log. Look at the graph in red. What does it look like the domain is for the red graph? 0 to infinity. And how about the range for the red graph? Yep.
All real numbers.
Yeah, it does keep going up. I know it looks like it flattens out, but it really doesn't. It kind of does something like this. It goes up extremely slow, but it does keep going up. Okay, so what I'm trying to show you is that if you know the domain and the range for an exponential, and you swap them, now you have the domain and range for a log. That's the connection. Okay. Any question on that? All right, so how do we write a log? Well, if you were doing it on lined paper, this is how it would look. That's y equals log. All of that would be right on the line. The a would be under it. The a is what we call a subscript. Just like an exponent is higher, well, this is something that's lower. It's a subscript. And the x would be right on the line as well. There are no exponents in what I wrote down right there. If I wanted an exponent, I could do something like that. Now I have an exponent. And the way that you read that, you read it left to right, just like how we read. And it's y equals log. Then you read the base number. Then you read what's called the argument. So it's y equals log base a of x. And what the base does is it controls what kind of log you are doing. Just like when you have roots. I can put a number here that controls the type of root. Right? Those are both roots. Right? The difference is one of them is a cube root, one of them is a fourth root. There's a bunch of different kind of roots I can do. Well, there's a bunch of different kind of logs you can do. You can do a base of 4. You can do a base of 5. You can do a base of 6. You can basically put any number you want in for the base. That's positive. It has to be a positive. So any question just on how to write that or how to pronounce it? Now, there is a base that we use quite a bit, and that's base 10. So when we are doing base 10, you don't actually have to write the base. You can just write the word log. And it's kind of like one of those things in math, like if you just put a letter, there is a number that's understood to be in front of that, but we don't normally write it. What number is in front of x here? 1. Well, same thing with this. If you just write the word log, and let's say you wanted to do the log of 12, there's no base in that box. That's okay. If you don't put the base, we will always assume it is a 10. And that's called common log. And the calculator has 2 logs that it can do by just pressing a single button. This is one of them. So if you wanted to actually know what the log of 12 is, press the button that's right next to the 7, all the way on the left. Log. And then you can type in 12 and then hit enter. So even though there is no base written right there on the calculator, it used a base of 10 to figure out this answer. Any question on what a common log is? And if you look at the answer that we just got, let's just look at it for a second. When I took the log of 12, I got 1.07918. Well, watch what happens if I take my base, which is 10, and I raise it to the 1.079181 power. Watch what you get. Anybody have a guess what you're going to get? Going to get 12.
That's not 12.
Yeah. Okay. So basically, this number that you get right here is an exponent. That's what that number is. What is it an exponent on? It's an exponent on your base. So we'll talk more about it, but I just want you to understand, anytime you press the word log, type something in, and you get an answer, that answer is an exponent. That's what a logarithm is. It's an exponent. Okay, there is one other special base, and you're actually looking at it right there. And it's when we have a base of e. Now, e isn't like a random letter in this section. E is a very specific number. It's about 2.7. And it's called Euler's constant, spelled E-U-L-E-R. Just like pi, that one's a little bit more well-known, but pi is a number we use quite a bit, especially anything that's spherical or circular in geometry. Well, we're going to use e in this section. And if you make that special number, that 2.7, and it keeps going, if you make that your base, that is called a natural logarithm function. It's also called a Naperian log. But I'll be using the word natural. Those are the only two logs that have special bases. Base 10 is called a common log. Base e is called a natural log. And those are the only two buttons the calculator has for logs. Right below the log, there's another button, and it says capital L, capital N. L, N. It's an abbreviation. So you generally will not see something like that, log base e. You're going to see an abbreviation. The abbreviation for log base e is LN. And that's it for abbreviations. There's no other logs that have special abbreviations. If you have a log with a base of 7, you just have to write log base 7. There's no special word for that. So this is exactly the same as that. This is how you'll see it, like that. And the button for natural log is right below regular log. One thing you have to remember when you're using these abbreviations is the abbreviation hides the base. So you've got to remember that ln means base e, and if you just see the word log without a base, it means base 10. Other than those two, you will always see the base rate. Yes?
So what's the base? The base for natural log is e?
The base for natural log is e, which is the number 2.718281828. It does not keep repeating 1828 forever.
Oh.
The next digit's different.
Okay.
It's like pi. It's just a number that goes on forever and never repeats, never has a pattern to it. It's irrational. Okay, and E, in case I didn't show you where it was, is the second division symbol. The calculator has E built into it, just like it has pi built into it. We already talked about all that. So if you wrote down the domain and range of logarithms on the other page, that's the same thing again. All right, so what we're going to do now is look at a formula that can convert from the kinds of things that we were working with on Monday, which were exponentials, to the kind of things we're going to work with today, which are logs. In this formula, there's nothing to calculate. It's more of just rearranging things and looking where they go. This formula can be used to convert either way, from log to exponential, or exponential to log. What's on the left is log form. What's on the right is what we call exponential form. What do we call this letter that's down a little bit lower from the word log? That's the base. And then when you have something that has an exponent on it, what do you call the thing that's lower than the exponent? It's also called the base. So that's why when you change from log to exponential, the base on your log becomes the base on your exponential. So the base stays as the base. Let's look at the y. So I told you earlier, when you type in log, I think I did 12, and you hit enter, you get a number. This number is a what? It's an exponent. So logarithms are always equal to an exponent. Logarithms equal exponents. That's why when you rewrite it in the other form, this becomes the exponent. And the last thing is that. What did we call the thing right here that's being plugged into the log function? Yeah?
The argument?
The argument. And the way you can remember where that one goes is if you argue with somebody all the time, you're going to end up all by yourself. So the argument ends up alone on one side. Okay, so that's the formula to convert between log and exponential form. And for the first 5 or 6 problems, that's all we're doing. Okay, so let's try it.
Can I use both ways?
Yep, okay, we're going to do some where we change to exponential, and then we're going to do some in a minute where we change to log. Okay, so it's just a matter of identifying the 3 things and figuring out where they go. And when you're done, you need something that looks like that. Those boxes are exponential form. You just have to figure out, let's start with this box. What do we call the box that's lower than this box? This is the base. What is your base in that problem? 3. So the base is going to be 3. Logarithm always equals what kind of number? Exponent. So the box in green, that is your exponent. And what do we call the x? The argument. And where does it end up? All by itself. And that's it. That's the answer. There's nothing we can solve there because we don't know y. If we knew y was 2, well then we could do 3 to the 2nd power and get the answer. But that's all you can do. Any question on the first one? All right, let's look at this one. So y equals log base 5 of x. So again, we're looking for something like that when we're done. What's going to go in this lower box on the left? 5, because that's my base. And the upper box? Y, because logarithm always equals the exponent. And the box that's all by itself, that's x. There you go. So that's again changing from log to exponential. Questions on that one? All right, try it the other way. Now they're going to give us something that is exponential, and we want to change to log form. Well, if we're changing to log form, what do you think the first thing we need to write down is? Yeah. Even before that. Yeah, we got to write down the word log. Okay, that's the first thing. If you don't have the word log, you don't have log form. So let's put the word log. And we'll have an equal sign. You can do it in any order. I usually start with my base. What's going to be the base on this log? Yep. 1.2, because that was the base for the exponential. So the base is 1.2. And logarithms always equal what kind of number?
An exponent.
An exponent. What's the exponent here?
3.
3. And the only spot we have left to fill in is the argument. And what's the only thing we haven't used that's by itself? M. So that's changing from exponential to log form. Any question on that? Try this one. E to the b equals 9. All right, so first thing that I should write down, log. Yep. What's going to be my base? Base is going to be an e. The logarithm is going to equal what? B. Always equals the exponent. And we need to fill in our argument, which is 9. What was by itself? Now, this one we can simplify a little bit. There's an abbreviation for all of that. What's the abbreviation for log base e? ln. And that one, you do have enough information if you wanted to get the answer. As a decimal, you could press ln 9, and it's about 2.197. Okay, they didn't ask for a decimal, so I'm not going to write that. But you could. So now, if you fill in 2.197 right here, and you take e to the 2.197 power, you'll get 9. We just solved for this exponent. That's what we did. Yes?
If they did ask for the decimal, would we just write the answer as b equals 2.197?
Yeah, there is one problem on the test. I might ask for more decimals, like 3 or decimals. But yeah, you just follow whatever they tell you to. If they don't, well, you go with 2, but I do tell you on the test. All right, let's try this one. So this one says to show that what is on the left is the same as what is on the right. What kind of equation is that? Log form or exponential? Log. What's the only thing that we know how to do so far with an equation that is in log form? Yeah?
Turn it into an exponential.
Let's change it to exponential and see if it's true. Let's start with our base. What's my base here? Yep, 2. What about my exponent? Three. Logarithm always equals the exponent. So there's my base, there's my exponent. And what do we call the thing that ends up by itself? Argument. And where's the argument in this? 8. It's right there. What's 2 to the third power? 8. So yeah, 8 equals 8. If we ended up with something like 8 equals 7, then that means the original statement was wrong. But because we got a true statement, we know it was correct. Any question on it? Okay, let's try this one. Log base 5 of 1/25 equals x. All right, what kind of equation is that? Log or exponential? That's log. And what do you think we're going to do to it? Yep. Could you change, Jack, could you change the whole thing to exponential for me?
5 to the power of x equals 1/25.
Yep, it was 1/25. Now, we've got to raise 5 to a power and get a fraction. If you had 5 to the x equals 25, it's not what we have, but if it was, what would be the answer to this problem? 2. 5 to the second power is 25. We want to get 1/25. What kind of number in an exponent causes it to flip and become a fraction? Yeah? Negative. So in this case, x would be negative, yeah, 2. So if you get stuck figuring it out when it's equal to a fraction, pretend that it wasn't a fraction and find the answer, and then just say, okay, I want it flipped, so just make the answer a negative. Okay, any question on that? Now, if this number it was not a power of that number, then we would have had a little bit of an issue. But for now, it will be. So we just solved for a problem where the variable was on the right. Now let's solve where the variable is the argument on the left. So the variable's in a different spot. Nick, can you tell me what this equation would be if we rewrite it in exponential form?
You'd have 5 as the base.
Yep.
You'd have 1.5 as the exponent, and you'd have x as the argument.
And that's it. We could do that out if they asked us to. They didn't, so I'm just going to leave it like that. So rewriting this in exponential form gets the letter by itself, and you're done. So when the variable is here, that's the easiest one. Any question on that? All right, let's try one more, and this time I put the variable in the third spot. Now it's the base. So we did it on the right, we did it as the argument. We'll finish up with it as the base. Okay. What would this be if you rewrite it in exponential form? Yeah?
It'll be 3 equals x squared.
So 3 is your argument, so that's by itself. X is your base, and logarithm always equals the exponent. So this time we're not done. We still have to solve for x. We have the squaring function. We need a function that is the inverse of that. What function cancels out squaring? Yeah?
Square root.
Square rooting. So we take the square root of each side. Square and square root cancel. And normally when you do a square root, how many answers do you get? 2. The square root of like 9 is 3 and negative 3. You can't use the negative answer. Okay? When we're dealing with arguments, bases, and arguments, these two numbers always have to be bigger than 0. Always. So when we take the square root of 3, normally you get 2 answers. Ignore the negative. Don't put a plus or minus in front of that square root like you do in the quadratic formula. Don't do that. Any question on that? Yes.
Why'd you flip the 3 and the 2?
Why did I flip?
Like usually,
Oh, you mean instead of writing it this way?
no, I mean the equation.
Instead of doing x squared equals 3.
Yeah.
Yes, instead of having the letter on the left. You mean?
No, I mean in the original equation, because if you were to put that in exponential, wouldn't it be x to the second equals 3?
Yeah,
Oh.
that's
Never mind.
that's what we have. Yeah. And whether you write 3 equals x to the second or x to the second equals 3, it's just a matter of what side the letter ends up on.
I was just getting confused.
Yeah. You could do it either way. Any other questions on that? All right, so let's look at some special properties of logs. These are patterns that when you see them, they're going to allow us to simplify something a lot. But they're special patterns. Let's start with this one. So if you had something like 5 raised to the log base 5, and just fill in a number right there. 12. The answer to that problem is very easy to figure out because it follows a special pattern. Whenever these two things match, like they do over here, the answer that you get is whatever is right there. So in this case, what would 5 to the log base 5 of 12 simplify to? Yep. 12. it's like the 5 and the log 5, it's like they cancel each other out, and all you're left with is the 12. You can check that if you're not sure. You could type in 5 raised to the log base 5 of 12. That's exactly what I just wrote down. When I hit enter, I get 12. Right? If this was a 5 and this was a 6, then no, it doesn't work. They have to be the same number. Okay, here's another special pattern. Log base a of a to the x. So this would be like log base 3 of 3 to the 15th power. Anybody have a guess what that would simplify to using property 2? Yeah,
Is it 15?
it would be 15. Yep. And if you want to check it, you could do log base 3 of 3 to the 15th power. And when I hit enter, I get 15. So it's a special pattern that when these two things match, everything cancels out except that. And that's the answer. Any question on the first two properties? Okay, third property. Log base a of a. This is saying that when you take the log and the base and the argument match, the answer is always 1. So what would log base 4 of 4 be? 1. It would be 1. And if you take this and rewrite it in exponential form, it makes sense why that always comes out to 1. Let's make this one a red A. What's my base? Which one? The red A.
Oh.
Yeah.
What's that?
So base is the red A. What's the exponent? Yep. The 1. That's what was by itself, or that's what our logarithm always equals the exponent. And what ends up by itself?
Black A.
The black A, because that's the argument. If you raise something to the first power, do you always get itself back? What do you think? If you raise something to the first power, do you always get itself back? Yes. That's all that this property is saying. This is the way of saying anything to the first power is itself. This is how you'd say it in like algebra 1. This is how you say the exact same thing as a logarithm. That's all that this means. Anything to the first power is itself. Let's see if we can figure out this. Log base A of 1. Log base A of 1. For now, let's just put, well, it equals something. We don't know. But yeah.
But it's just equal A.
Well, let's see. What's the base? If we change this to exponential, what's your base there? A. What's your exponent? The question mark. And what ends up by itself on the other side? 1. What power can you raise something to and always get 1 is the answer? 0. Yeah. 0. So this is saying that when you take the log of 1, the answer is always 0. Doesn't matter what the base is. And this is the rule from algebra 1 that anything to the 0 power is 1. This is how you write that as a logarithm. let's try a couple more of those. What property is that? Example 6a. Yeah, it's the first one. So if you simplify it, what are you going to get for x? Pi. Yeah. You get pi. So 3.14. How about b? What property is that one most similar to? That's the second one. And if you use property 2 to simplify that whole thing, you will get a single number. -4. Okay, how about that one? ln of e to the kt. Anyone see what property that was? It is property 2. How could we rewrite that so it makes it a little more obvious that it's property 2? Yeah?
Would you change the ln to log base e?
Yeah, change the part that I circled to that, and now write the rest of it. And what would we get when we simplify that? K times t, whatever that is. Yep. Okay, and how about log base 3 of 1? Yeah. Yes, I was going to Nico, but yeah, go ahead. Yeah, you can go ahead, Christian. What did you say? Property 4, which means it comes out to 0. Yep. So those are 4 special properties of logarithms that don't really involve any math. It's more of recognizing a pattern and simplifying based on a pattern. Any question on that? So, last thing. Okay, so the last thing we're going to look at is properties that allow us to take 2 logarithms that are separate and combine them together, or take 2 logs that are already together and split them apart. And here's an example of the first property. First property deals with having a product of, you can have 2, 3, you can have more than 2, but I'm just doing it for 2. But when you have a product of 2 things multiplied together inside the argument to a log, that splits as a sum. When you split it as a sum, you started with 1 log, now you're going to write it 2, because you're splitting it apart. The base on each log when you split it apart is exactly the same as the base you started with. You can't change the base. The first argument is your first factor. The second argument is your second factor. Right? So I'm not going to type this in, but if you did, you would get exactly the same thing on the left side and the right side. So a product turns into a sum. For rule 2, we have, instead of a product, we have division. What do you think division is going to turn into when you split it into 2 logs? The difference. Yep. The thing we have to remember about the difference is subtraction is not commutative, so the order is important. It has to be the log of what was on top minus the log of what was on the bottom. It has to be in that order. Top comes first, bottom comes second. Base stays exactly the same as what it was originally. Okay, so that's a property that allows you to take a fraction inside of a logarithm and split it into 2. Any question on the second property? third property. Third property says that if you have an exponent on an argument in a log function, you can take that exponent and put it in front. And that's the third one. So exponents inside the argument to a log function can go in front.
Mr. Hager,
Yes.
is that a line sign? Like it's log A, is that a line sign? Is that supposed to be?
Oh, I think maybe that was just when I was,
Okay.
I think my hand probably hit the board, yeah. So when we do these problems, you might see a question that says to split into logs and don't leave exponents in the answer. If it says not to leave exponents in the answer, you move them in front. So now this is where some people mess this up. If I said to you not to leave exponents in an answer, and you left something like this, you left an exponent in the answer. When you take the square root of something, square root really means to what power? Anybody remember?
Power?
What power?
2.
So that's squaring. That's to the second, but square rooting means to the
1/2.
right. So this means you really left the problem like that. You left a hidden 1/2 as the exponent. It's hidden in that symbol. That 1/2 should really go where? In front. So if you see a problem and it has a square root in it, you're better off to change that square root to the 1/2 power so you remember it is a hidden exponent. Okay, this doesn't use properties 1 or 2. This was just property 3. But it's like a hidden example for property 3. Okay, so those are all the properties for combining and splitting, and now we'll just try some combining and splitting. And that's it. So this one says to separate the log into multiple logs, express powers as factors. That means do not leave powers in the final answer. Put them in front as multiplication. Okay. How many logs is this going to split up into when we break it apart? 2. We're going to have a log and a log. What's going to be the base on each one of them? Base 4. Are the 2 logs going to be added or subtracted?
Added.
Yep. Yep, they're going to be added because it was multiplication. And what's going to be the argument to the first log? 3. And the second log? X. So that's how you take one log and split it into 2. Let's try this one. How many logs is that going to split up into when we break it apart? Yep, it'll be 2 logs again. What will be the base on each one of them? Yep, same as the base you started with. The log is going to be added or subtracted. They're going to be added because you have multiplication inside. And what is your first argument? 5. And the second argument? R cubed. Now we would be done if it didn't say express powers as factors, but you left a power in the final answer. The first part's fine. How are we going to fix the second part? Yep.
We bring the exponent or argument over
Yep, so what would you have?
It would be 3 log base 2 r.
Perfect. Questions on it? Yes?
When is it subtraction? Or actually about subtraction? Okay.
All right, so log base 9 of x divided by 2. We're going to split that apart. How many logs are we going to have when we break it up? We're going to have 2. What's the base on each one? 9. And because we had division inside the argument, what are we going to do with the 2 logs? We're going to subtract them. What's going to be the argument to your first log? X. And argument to your second log? 2. And that's it. Okay, so we did, I mean, it works with any base. You just have to keep the base the same the whole time. We did base 4, we did base 2, we did base 9. What base are we doing now? E. You don't have to write log base E though. You're going to use the abbreviation, LN. Anybody think they can do that whole thing in one step? And tell me final answer. Julia?
3 ln to the base of, like, yeah, y. No base, but
No
y.
base, the base is E. So yeah,
Plus.
3 ln y.
Yeah, plus.
And then we have a division sign.
Oh, minus.
Minus
ln.
ln 8. Yep, 3 ln y minus ln 8. So any questions on the splitting part? Okay, so now we'll do the combining. So it says combine the following into a single log, express factors as powers. So now they're telling you if you have something in front, put it back as an exponent. So we're doing everything we did in reverse. Okay. So if we're going to do everything in reverse now, what do you think the first step in this problem would be?
Log.
Think about the last step you would have done if we were doing this like we did the other problems to get to this point. What would you have had right before this step? Yeah,
Would it be, do you want the whole thing or just the first step?
just the first step.
You do 3 to the 4th power.
Right, we're going to take the 4 and we're going to put it back as an exponent. So log base a of 7 plus log base a, and what's 3 to the 4th power? 81. Yep. Okay, now I want to recombine it into a single log. What's going to be the base on my new log when I recombine it? Yep.
Log A.
It's going to be base A. On base A. And how are we going to recombine the 7 and the 81? Yep.
Is it 7 divided by 8? Or 7 times 81?
So that's the question. Do we multiply them or divide them?
Never mind. Ask somebody else.
Yep. We multiply them because it's addition. 7 times 81. Just put that right there. And then that simplifies to 567.
Did you just do that in your head?
Yeah. Well, it really wasn't too hard because I just thought of 81. I think of it as 80 plus 1, like that.
Oh.
So then I thought of 7 times 8 is 56.
Okay, that's fair.
Plus 1 more. So 567. 567.
Still crazy.
That's how my mind works. All right, let's just change this a little bit. Is this the last one? Yeah, last one. Okay, what is the first thing that we would do to the first log?
2/3 to the exponent of it.
Yeah, put 2/3 back as an exponent. Okay, we'll come back to that. And then here they've given us a calculation. We should just simplify it. We just did 3 to the 4th. That was 81. It's 81 minus 71. 10. Now, 8 to the 2/3, even though that's a fraction, that's not that hard to do in your head because of the numbers. That means to take 8 and raise it to the second power. And when you divide by 3, that's a root. What kind of root is it? A cube root. So what's 8 to the second power?
64.
64. And now what's the cube root
8.
of 64? 4. You could also do it the other way. You could take the cube root first. What's the cube root of 8? 2. And what's 2 to the second power? 4. You can do it that way too. Minus ln of 10. And when we recombine these, we're going to have a single ln. And what are we going to have inside that? Parentheses. Yep.
4 over 10.
Yep. You're going to have 4 over 10, which reduces to 2 over 5. And that's the final answer, fully simplified and recombined. Okay. Any questions on that? All right, so that's 5.4, part 1, and then tomorrow 5.5 isn't any longer than what we did today. Actually, might be a little shorter. All right, so on 292, those are the questions for tonight. Some of them are very quick, just changing exponential form to log form. So just make sure you show your work for anything you need to. Reminder, tomorrow I will be after school for extra help. And Friday we'll have our test on 5.1, 5.4, part 1, skipping part 2, and 5.5.